That would be good.
Yeah, there is one here somewhere. Oh, there it is. Right here. It's a spider hunting.
Yeah, got it. Okay. So I'm going to tell you about Dawn. It's the mission that brought those annoying bright spots. Okay. So I need to, okay, which way do I, okay. And so I will, that's not going to do it. How do I get rid of this annoying? Oh, okay, it's gone. Oh, it's on my screen. It's not on your screen. Okay. Dawn is a solar electric propelled spacecraft with a very small payload. It comes with a framing camera, gamma ray and neutron detector, and a visible and infrared mapping spectrometer. And it also obtains gravity data from radiometric tracking. It has been going through the asteroid belt. It stopped at Vesta and mapped that for a little over a year. And then in 2012, we left Vesta and made our way over to Ceres, and we got into orbit in March of this year. And when we got into orbit, we went into this circular orbit, which we call rotational characterization, and that was a 15-day orbit, and we took data from 14,000 kilometers. It was not great resolution, but it gave us the gravity data that we needed in order to navigate around the body, and it gave us a good first look at the surface. And we've been spending some time looking at that data, but after we took that, we made our way from the rotational characterization orbit into the survey orbit, which is a little over 5,000 kilometers from the center of Ceres, and a 75-hour orbit. And this is what I'm going to report on today. And later we'll get into HAMO in late summer, early fall. And then in January, we will go down to our final orbit, LAMO, at an altitude of about 375 kilometers and 5 hours orbit. Now, the survey orbit is optimized for the VIR infrared and visible measurements. HAMO will be optimized for the stereo photogrammetry, and LAMO is where we will get our best gravity data and the gamma ray and neutron detecting. So we'll do the geochemistry down in that last phase. And as I said, we finished RC3 and we finished survey. Now here's what we do in the survey orbit. We orbit in a polar orbit and then snap figures with our framing camera and scan with VIR. And the VIR images in little cubes takes a spectrum of 200 and odd samples across the surface and a similar large number of spectral samples, and then that push brooms across the surface for some segment. And we've covered most of all of the surface in survey, except that we had some periods where the instrument was not operating, and it's left a hole in our favorite spot on the surface. The physical properties, the important thing is that the obliquity is what we thought it was, but it was pointing in a different direction. So winter is summer and summer is winter in the northern hemisphere and the southern hemisphere. And that fooled us a little bit, but the obliquity being small, it doesn't make a big difference on the lighting on the planet. The most important difference in the physical properties are the size is smaller than we expected it to be from the HST measurements. That pushes the density up about 4% from what we thought it was. So it's a little bit denser. We've taken and made taken pictures of the whole surface and made mosaics of them, and we've been putting down the names that the IAU has designated for this body, which is harvest deities. It took us a while to get a vetted list of proper deities, but we're doing fine now, and this list has been approved by the IAU. That was the elevation. Let me just, so you can see that there are lowlands and highlands and lots of craters, and we'll get more into that in just a minute. Could I have the movie? Okay, so this shows the rotating series. There's those bright spots. You can see there's lots of craters, but if you're very fast and counting and sorting, you'll find that there are not as many large craters as you might expect. So we're missing the large craters as if that they have been able to recover or they never were formed, possibly, but probably that they were formed, and those large regions of scars were not preserved on this body. Let's take a look at some of the surface features. The geologists have had a field day on this body thus far, looking for their favorite type of geological formation. There's, of course, a lot of craters, and there are a lot of craters of different types. There are simple craters that just, an impact takes place and excavates. There's central peak craters, and there are craters with central pits. Now, central pits have been found before on other bodies, but there are a lot of central pits on this particular body, and that's telling you something about what the surface material is like. So we have a lot of surface pits. The craters are not all circular. They're almost every shape you can imagine. There are hexagonal craters, irregular craters, degraded craters, joined craters, and of course there are a few rayed craters like on this particular slide. So you'll have a field day if you like different types of craters. We have pit chains on the body, possibly due to fissures and material falling down, or possibly other causes. This is the famous bright spot crater, and we'll get to take some better looks at that in just a moment. There are ridges that are around the edges of large craters, but there's also ridges that seem not to be associated with a crater. There are fissures on the surface. There's strings of craters, as we've seen before. The largest crater that we've sort of officially designated is the Lodi Basin here, and that is the largest crater that we've been able to identify as a crater. We may, after we make a shape model, find some more, but right now that's our large one. There's lots of strange linear features on the surface all over the place. And What's causing these things is not clear to us just yet. There are landslides in many of the craters. This is an odd one sort of oozing across the surface here. Another one over here. So there are lots of flow-like features and mass wasting in these craters. We have one mountain. We only have one large mountain. It doesn't mean we don't have irregularities on the surface, but we have this mountain that we don't quite understand. So we called it the pyramid. It was sort of multi-sided shape. We'll take a look at that in just a minute. It's fairly high. It's about 3 miles or 5 kilometers in height here. And we haven't got good spectra on the surface just yet, but we will eventually do that. Could I have the movie here? And so this is the pyramid, and it's got, yes, white sides and much around it. This is part of this is lighting, but it's got white sides on much of the surface. And just looks like the material's cascading down from above. Then this is not the sun. The sun has facula on it, but we have facula on Ceres, and the geometry of this of these spots is kind of interesting. There's right in the middle. And you may say, well, that's the very center of the crater. It might be. And there's a very large white area. And then there's a bunch of little spots around. And anything that's that bright and small seems to me as some indication of transient behavior. Is it is there action of water? Is it salt deposited on the surface, or is it something else? And this is our major mystery, although the pyramid also has us surprised. By the way, that Alan Stern is very competitive, so when he saw that mountain, he found a whole mess of them on Pluto. So our interpretation is they're exactly the same phenomenon as that Alan came to tell us about the other day. Okay, could I have the last movie? So this is the bright crater, and we'll go around it. You can see that the floor is covered with this white deposit, and this region has a lot of the white deposits, and there's smaller regions there. And the craters themselves are interesting. The walls, the steepness of some of the slopes here. It really is going to be an interesting body, and one that has evolved, I think, a lot with time. When you look at this crater, though, it is interesting for several other reasons. We do see haze in this crater. Not now from this vantage angle, but in the noontime, and if you look at a glancing angle, you can see what seems to be haze, and it comes back in a regular pattern. So this, this central pit here, or these other bright spots over here, are possibly subliming, or they're providing some atmosphere in this particular region of Ceres. We also see atmosphere sort of from reflected light around the dark limb. And we haven't sorted through all those things, but this body is going to be very interesting. So Ceres is our prototype wet protoplanet. It's intact. It's been there since the earliest days of the solar system. But I would say, unlike Vesta, it's had a lot more evolution. It's the most massive body in the asteroid belt, and I would claim it's unlike any other solar system body. It's unique in many of its properties. Whatever the cause of the bright spots, they indicate activity on Ceres. So it is perhaps the largest main belt comet out there. Certainly the largest asteroid, and it seems to be having comet-type activity. But it's important to us because there is a lot of water on this particular body from its density and from what we're seeing. It possibly it's akin in the early solar system probably brought us our water supply on Earth. So it's important for us to go and learn about what Syria is like just for that purpose. But also it is possible that the water systems associated with Ceres may harbor life and could be conducive to life more than some of the outer solar system bodies. So I would say we really do need to spend some time in probing the surface of Ceres and checking out its astrobiological implications. Thank you.
That was so exciting, I could hardly tell him to stop. So I can take one question. Okay.
It's not 12 yet. The hand is not, the big hand isn't on the 12
but
yet.
I figured it's going to take that long.
Really interesting results. Do you have an idea of, Dana Hurley from APL. Do you have an idea of the scale height of the haze feature that you're seeing, or spatial extent at all?
Okay, well, it covers, let's say, about half of the crater when you look on the edge on. It stops at the rim. It doesn't extend over the rim. It's trapped in the rim.
Very interesting.
Someone else can try speaking. Go ahead.
Yeah, could it have the same dust clouds as the lunar surface electrostatically?
I have no idea what the electrostatic properties of the surface are. So you can speculate. That would, and we've been saving all those speculations. I get them every day. If somebody actually gets it right in that group, we will probably give them some sort of an award. But yeah, I think I will put that in with my others.
Very good. Thank you so much, Chris.